nothing up here. Okay, so chapter 14. First thing is first, we're going to relate this to past chapters and what we've done. So conjugation and aromaticity. We talked about that a little bit. So, one second. Could you Sorry. Okay. So we talked about conjugation versus aromaticity, right? And we mentioned that aromatic rings are much more stable than conjugated ones. So in general, I'm going to give this to you as a rule now. Conjugation is more stable than not conjugated, but aromatic is more stable than conjugated. And another thing that Dr. West talks about for ever in the things, he gives a really, really good in-depth explanation of the energy diagram for benzene. We're also going to talk about it, but not as in-depth. But essentially, the summary of what he's saying is that we have, I'll write it over here. This is what benzene looks like, right? And let's say we have energy here, right? So the energy for a cyclohexane is up here, right? And then the energy for a triene, so 3 double bonds in conjugation, is let's say here, right? Because trienes are super stable, because conjugation makes it super stable, right? But the benzene ring, because of this extra stability, extra aromaticity, instead of being up here, it's actually going to be all the way down here. So the expected stability of benzene is here, but the actual stability is here. And someone mentioned this, and I forgot to mention just a hexane. So this is just a hexane, regular carbon chain, really high energy. If you have a triene or cyclohexatriene, which is another name for this, cyclohexatriene, this is what you expect benzene's energy to be, but it's actually all the way down here. So we can say that benzene exhibits higher stability than what is expected from cyclohexatriene. And I don't know why there's a question mark, but that's fine. We know that it's higher. And we actually have 3 fun little terms when it comes to aromaticity. There is aromatic, not aromatic, and anti-aromatic. We're going to go into what each of those means, and then we'll come back to ranking them in order. So I have this criteria, area for you guys to write, but I find that I don't ever have enough space when I use that. So I'm going to open up a different page, but you guys can follow along and write the answers here as I talk. And then if you need me to clarify anything, feel free to let me know. So the first one is aromatic, right? That's the whole point of the chapter. We'll go over that first. And then we have non-aromatic. And we have, sorry, my screen is being really weird the past couple days. And then we have anti-aromatic. And just for shorthand in the future, because I don't like writing that out every single time, this will be AA, this will be NA, and this will just be A for aromatic. So there are 4 rules to be aromatic. Rule number 1, and these are not in any particular order, but I prefer to go in this order. So 1, it has to be cyclic. So it has to be a ring. That one's pretty straightforward. Rule number 2, it has to be planar. And pretty much always it will be planar if you have rings that are smaller than 8 members. So I'm going to write a little star here. Rings with 8 plus members may not be planar. So you can pretty much always assume that it's going to be planar if it's less than 8 members, but once it's more than 8, that's when you got to pay attention. 3, and I know I'm super zoomed in, I will zoom out at the end. 3, it has to be fully conjugated. And can someone remind me what fully conjugated means? And if you don't completely know or you just kind of have a guess, that's 100% okay. But this is a concept from the last chapter, so I want to see what you guys think.
A single bond between double bonds?
Exactly. So fully conjugated means that we have double bond, single bond, double bond, single bond. Another way that we can state that that's important for this chapter is it must be all sp2 hybridized. And what that also implies is that it is fully delocalized. And I think that's a term that you heard in Orgo 1, but essentially delocalization just means that all of the electrons are going to resonate across the whole molecule. So the electrons are freely moving around the whole thing because it is fully sp2 hybridized. And one thing I want you guys to remember from the last chapter, what are 2 things that we consider sp2 that we learned about during molecular orbital theory? Adjacent to a double bond, but yes, but more specifically, what were the 3 conditions? Cations, radicals, and anions. Exactly. So cations, anions, and radicals are sp2. So remember that they are sp2. And rule number 4, which is arguably the most important rule that you guys have to learn, it's completely new, is the 2n. Oh, just kidding. I lied to you. I'm sorry. The 4n plus 2. Oh my gosh. Wow. Start over. Okay. Rule number 4 is the most important rule that you guys have to know. It's completely new. And it is the 4n plus 2 rule. And I'm writing that for the first time. So it is the 4n plus 2 Pi Electrons Rule. And this is also called Huckel's rule. I think it's actually Huckel, but I'm not going to say that. And I want you guys to just pretend nothing you've ever learned exists prior to what we're talking about now, and just pretend your brain is empty and just listen to my explanation, because a lot of people get confused at this point. So the 4n plus 2 rule, if you know anything about math, implies that this n right here is a variable that you need to know, and it's going to be a number, and you have to get that and plug it in and do the math, right? Wrong. Technically, yes, there is a way to do that, but you can't just be given a molecule. Like, I'm not going to give you benzene and say, hey, what's n? Figure out Huckel's rule, right? You're never going to be given n. N is just any real number. You can submit any whole number. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, whatever you want it to be. So I'm going to go ahead and give you guys a little cheat sheet, or not cheat sheet, but like a little cheat here. So any number 2, 6, 10, 14, 18, etc. are all going to follow Huckel's rule. And in case you have no idea what I'm talking about, which I'm sure you don't because what the heck does any of this mean? Let's say I give you a benzene ring, right? We are going to count the number of pi electrons. And I'm going to draw out each of the pi bonds since we're doing this for the first time. You definitely don't, wow, that's ugly. You definitely don't have to reproduce this. I just want you guys to be aware. And we know that for double bonds, we have 1 electron in each of these orbitals. So altogether, please tell me how many pi electrons we have in benzene. Also, someone said, so even numbers? No, don't think even numbers. Yes, that's technically true, but I don't want you guys to think about it that way, and you'll find out why in a second. So you guys are saying in the chat, exactly, so there are 6 pi electrons. And so this follows Huckel's rule because 6 is a multiple of 4n plus 2. And aka it is one of these numbers. So since 6 is one of these numbers that I've given you right here, this follows Huckel's rule, and it is aromatic. Any questions on these rules? I know the 4n plus 2 gets really tricky for people. It sucks. So let me know if you have questions. Cool. So we are going to skip non-aromatic for a second, and we are going to go to anti-aromatic. I know I drew it in the middle, but trust me, there's a method to my madness. So anti-aromatic, let's feel purple today. And then someone said, so basically +4 after the number 2. Essentially, yes, I would pretty much say, if you're going to think about it that way, think about it as a multiple of 4 plus 2. But what you said, yes, was correct. I just said it, worded it slightly differently. And someone said you need all 4. Oh, sorry. Go ahead. What's up?
So could you write an example that wouldn't follow that rule?
Yes. I'm going to do that for these two. If you still have a question, ask again. But hopefully that'll clear that up. And then someone said you need all 4 to be aromatic. Exactly. So you need to follow all 4 of these rules to be considered aromatic. So anti-aromatic also has 4 rules. And it can be a little bit tricky sometimes because the rules are cyclic, 2 is planar, 3 is fully conjugated. So far, they're exactly the same. The difference is rule number 4, because this is the 4n pi electrons rule. And so all that means is now instead of Huckel's rule, where we have 4n plus 2, now we need a number of electrons, or excuse me, a number of pi electrons that are a multiple of 4. And again, I will be so nice, and I will give you those numbers. So 4, 8, 12, 16, etc. If it's more than 16, odds are it breaks another rule. So So someone asked a question, and is 1 plus. I don't know what you mean.
No, I just mean it's 4 plus because you just have like 4 in pi e.
Oh, okay. Yes, okay. Pi e just means pi electrons. So we're talking about like this number, 4n or 4n plus 2. Excuse me. 4n plus 2 is just telling us how many pi electrons there are. So you can almost think of this as being your variable or your unit almost.
So for this one, it's not 4n plus pi e, but the other one is. Okay.
Yes, but even in this one, this is separate. So like it's not plus 2 pi electrons, it's just 4n plus 2, and then the what is it called? The units are still pi electrons. But I'm glad you pointed that out because I think a lot of people must have had that question. So yeah, pi electrons is essentially just like X. It's just there. It's just telling us what we're looking at. So like if I say 2 meters, 4n plus 2 is the number, and pi electrons is the unit. So it's like saying 2 meters. Does that help a little bit? I hope. Okay. So now that we have our rules for being anti-aromatic and aromatic, let's do non-aromatic. Non-aromatic is actually super simple. That's why I left it for last, because the rule here, and let me actually just draw a line before I do that so that it's not confusing. So in order to be non-aromatic, you literally just break any of the 4 rules, aka not cyclic, not planar. That's not an N. I don't know what language that was. Not planar, not fully conjugated. And what I mean by not fully conjugated is anytime you have an sp3. So if you have an sp3, it's not aromatic or anti-aromatic. And the last one is not being 4n plus 2 or 4n pi electrons. So if it's neither 4n plus 2 or 4n, that means it is not aromatic. And then someone asked in the chat, while you guys take a look at that, does anyone know what chapters are on the next exam? I believe it's just going to be 14, 15, and maybe half of 16. But that's just my guess. You're welcome. Okay, so any questions so far just on this introduction kind of thing? These are just the rules. I know some of these things might not 100% make sense because you haven't seen an example with it. But conceptually, I want you guys to know aromatic equals cyclic, planar, fully conjugated, 4n plus 2. You have to have all 4. Anti-aromatic means cyclic, planar, fully conjugated, 4n has to be all 4. Non-aromatic is any time you have any of these rules broken. So not cyclic, not planar, not fully conjugated, not 4n plus 2, not 4n, or anything else you can think of. Now that I have given you those rules, there's also a couple rules that I have made up. And actually, I'm not going to say it like that because that sounds like this is all just me making stuff up. What I mean by that is these are the technical rules, but then I have my own personal rosemary rules because through my experience, I've learned that there's just stuff. And hold on, I just had a stroke. These are the rules that they give you. These are the actual technical rules that you get in the textbook. But through my experience, I know that there are other concepts and stuff that become much easier to understand if I give them to you as a set of rules. So that's what I'm going to do now. Also, someone asked for the sign-in sheet, and I sent that again. So I will title this part Other Rules. And they're mostly about heteroatoms. And someone please remind me, what is a heteroatom? Oxygen, nitrogen, sulfur, exactly. So it's essentially any electronegative atom. It could also be like phosphorus, pretty much anything that's not carbon or hydrogen. Sweet. So, yeah, that's pretty much all I want for that. So the first thing I want to mention, and let's do pink, because why not? Heteroatoms can be either sp2 or sp3. And I'm going to say they can choose to be. And we'll explain what all of that means. I also want to mention that only one pair of electrons can count max. The second rule is that multiple single bonded heteroatoms must have the same hybridization. This is like low-key kind of awkward because when I'm filming these for you guys, I just press pause in the recording and then I write, so it's not like an awkward silence. Embrace the awkwardness, though. Must have. Also, while I write this, I will tell you a fun little side story that makes no sense to what we're talking about. I went to Starbucks with Chris the other day, and I saw one of you guys, and it was so funny because you were like, oh my gosh, hi, Rosemary. And I was like, oh my gosh, hi. And basically, I felt like a celebrity, so thank you. All right, so you will kind of understand what this means more in a little bit, but again, just want to give you the rule. The next one is double bonded heteroatoms must be sp2 hybridized. So double bonded heteroatoms must be sp2 hybridized. And that makes sense because anything that is double bonded has to be sp2, right? And so what that means is, additionally, it must donate one single electron. The other oxygen rule is actually, that one will not make any kind of sense at all until we start an example. So I'll give that to you later. So I'll leave a spot open for that, and I'll give it to you later. The last rule I'm going to give you now is about boron. So the boron rule is that boron is always sp2 hybridized. And it will always donates 0 electrons. So usually, if it's sp2, it will donate 1 lone pair, but boron is the exception. It will never donate any electrons. It will always be 0, even though it is always sp2. So I will zoom out and let you see these rules. Please let me know if you have any questions so far on these rules. I know I said we're going to go into it, but if there's anything that you just straight up like, you're like, what the heck do any of those words mean? Let me know. If not, let's get into a couple practice problems. Someone said makes sense so far. Yay, thank you for the validation. So, this might not seem like a lot, but this is the holy grail of aromaticity. If you can do every single one of these by the end of this, you are golden for aromaticity on the exam. And we will go through all of these, probably multiple times, in painful detail until you can recite all of my words back to me. That's how serious I am about these practice problems. So we have 5 minutes. Let's go through like the first row or so. Alrighty, so the rules again, I'll just put in the side. 1 is cyclic, planar, fully conjugated, and 4 is 4n plus 2. So I want a lot of participation for these, and it's okay if it's just guesses at first or you're just kind of getting into it. Still want participation. So is this cyclic?
Yes.
Yes. Is it planar?
Yes.
Yeah, question mark. It's not more than 8 carbons, so we don't care, right? Is it fully conjugated? So remind me, what does that mean? Someone did say no, so yes, awesome. Yes.
I was saying that it's all sp2 hybridized.
Okay, so this one is sp2, this one is sp2, but what about this one right here? I don't mean to put you on the spot or anything, but this
It's sp3, right?
It is sp3, yes. So this carbon is actually sp3 because it's not double bonded, no carbocation, anion, or radical. And people get this one wrong all the time. So pay attention. All right, so it broke one of the rules, so it must be what? If we scroll back up here.
Non-aromatic.
Non-aromatic, exactly. And for the first couple, I'll actually write it out, but then I get bored after a while. So not aromatic. But just for funsies and for practice, let's go ahead, let's go ahead and count the number of pi electrons. So we know that each double bond is contributing 2 of them, aka each double bonded carbon contributes 1. So how many pi electrons do we have?
2.
2, exactly. Because we have 1 from this carbon and 1 from this carbon. So there are 2 pi electrons. So would this fit the 4n plus 2 rule?
Yes.
Yes, and that is because n could be 0. So if it's 2, it does follow this rule. But this is not aromatic. It doesn't matter if it's 4 pi electrons because of this sp3 carbon. But that idea is really, really Someone asked me to go over counting again, and I will do that for this next one because it's almost the same. So I'm going to go ahead and draw this. So these are the pi orbitals. Each of the pi orbitals in the double bond has 1 electron, and this dashed line is the double bond shown in 3D. And we know that a cation has an empty p orbital, right? So let's go through the list. Is this cyclic? Yes. Is it planar? Yes. Is it fully conjugated now? Yes, because now this is for sure sp2. So now we got to count our electrons. And I'm going to go over that again in blue. So we have 1, 2, and this pi bond is empty. So altogether we have 2 pi electrons. And the 2 ways that we can think about this are, 1, you could either say that each double bond contributes 2 electrons, which is just easier for some people. The way I like to think about it is each double bonded carbon contributes 1 electron. And that's what we've essentially drawn out here. And we've shown that each one of these carbons contributes 1 electron. So whichever way works for you, whichever one makes more sense, you're going to get the same answer. So just keep that in mind. Is that a little bit more clear as far as counting goes for these 2? Yay, okay. So now we have the anion. So someone remind me in the chat, how many electrons are going to be in this anion orbital?
I have a question real quick. And I think there's going to be 3. But for the one prior, for the 2 pi electrons, so are we saying that it does follow the 4n plus 2 rule because it would be 10 and 10 was one of our numbers, or?
So I think you're taking this number and filling it into the equation, right?
Yeah.
Yes. So while that makes sense, and that's what a logical person would do, unfortunately, that's not what we're doing. So all you're going to do is count the number of electrons, and if it equals one of these numbers, it's aromatic, and it follows that rule. If it equals one of these numbers, it's anti. Yep. And that's why I said you have to pretend like nothing else matters, because logically, who would do that, right? That makes no sense. And yeah, I forgot to mention, so thank you for asking that question. This one is aromatic because it does follow the cyclic, planar, fully conjugated, and 4n plus 2 rule. What did I even write here? I promise I am literate. Okay, so back to the anion one. I forgot what you guys had said in the chat, but if it's a negative charge, this carbon will have 2 electrons, right? Because like we did in the last chapter in molecular orbital theory, cation is empty, radical is 1 electron, and anion is 2 electrons. So at this point, is this cyclic? Is it planar? Is it fully conjugated? Cool, so how many pi electrons are there? You guys tell me and then we'll go through and count them together. 4, exactly, because 1 per carbon of the double bond, and then 2 from the anion. So 4n No, I lied to you. 4 pi electrons, right? And so does this follow Huckel's rule? No. Which rule does that follow? 4n, exactly. So it's anti-aromatic. Yay. Okay, so I just wanted to go through at least those 3 examples with you guys today so you could just see what I mean by the counting and those kind of rules. We will go over all the other rules and all the other problems next week. I promise we will go through every single one until you are sick of me hearing these words. But someone asked, why would this be anti-aromatic? And so I'll go over that one more time. So it's cyclic, planar, and fully conjugated, right? Because it's a ring. It's planar because there's less than 8 carbons. And it's fully conjugated because it's all sp2 hybridized. And then if you count the number of electrons, so all of the electrons in these p orbitals are going to count. So we have 1, 2, and then the anion has 2 electrons. So it's 4 pi electrons. And so if we look at the anti-aromatic rules, we're looking for multiples of 4. So 4, 8, 12, 16, etc. Sorry for zooming so fast through these, like the pages. So that's why we would call this one anti-aromatic. Does that make a little bit more sense? And yes, Angel, all of them would, all of these would still be sp2 because it's an anion, and so that will count. So yes, that is my intro for you guys today. Someone wanted to talk to me. I didn't forget, haha. So I will be here. I'll stay on. If you have any questions, please feel free to stay on and ask me. If not, I will see you guys next week. Again, I'm so proud of you. You guys are doing great. Even if you didn't get the score you wanted, I still believe in you. You're still working so hard. I see you. I appreciate you. You guys are great, and Bear thinks so too. So that's all that really matters.